So today we are going to talk about Ethereum Virtual Machine. I believe we all know what Ethereum is. Ethereum is like one of the second blockchain that have ever created after the Bitcoin. And so Ethereum actually adds a more functionality rather than just having financial transactions. Ethereum actually allow you to execute code over the blockchain. So that is the USP for this particular blockchain that when it comes, right? And for that, it basically uses a concept which is known as Ethereum Virtual Machine. Right. We'll be talking about that today, and we'll be understanding how it works and how code executed on chain on the blockchain. Right. So yeah, we'll be covering that today. Let's get started. So let's start about what Ethereum Virtual Machine is. So how Ethereum network actually works, let's talk about that first. So Ethereum network is made up of multiple computers. So if you have ever heard about torrent, right? So torrent has those seeders and leeches available on the network. So what those seeders are, those are basically the computers that are connected to the torrent network, and they were basically seeding the data so that you can access your file. So this is somehow similar, right? So how it works is like there will be a network, right? And there will be a lot of like I would say millions of computers are connected to that network, right? And every other computer is considered as node. So you can see, like I have mentioned, that each of these computer is called node, right? And every node basically runs a software. So it is a special software which is known as Ethereum client, and that software help that particular node to communicate with that blockchain, right? So inside each node, the Ethereum virtual machine executes smart contract and processes transactions, right? So how it works is like when you basically want to like make any changes in the blockchain state, you have to send a transaction, and that transaction get processed by any of the connected node, and then it get updated, that the state of the blockchain get updated further, right? And we will talk about in details like how it works and how basically things look in the picture on the engineering side of the things, right? But yeah, let's go. So as you can see, all nodes work together in peer-to-peer network. So we basically call it P2P, and Ethereum network is like, definitely secure and decentralized. So here I have added some example diagram like how it has works. Like multiple computers are connected to the network, and yeah. Now let's talk about understanding the blockchain transition state, like how blockchain actually transition its state. So there will be some building blocks of the blockchain, and we will be talking about that. Okay, so there will be first building block, which is itself named as block. A block is basically a container that hold a snapshot of Ethereum network at a specific point of time. So consider like if I consider a block right now, right? So it can take the timestamp of current state, and it can include the state of the blockchain. Suppose it can include account balances, it can include contract storages and many more things, right? So and it holds a specific snapshot of specific time, right? When we talk about time, right, so we understand that there will be states. Why? Because so at the current time the state will be something different, but in future maybe 10 minutes later new transaction will be added and the state has been manipulated, so there will be a new state, right? So we understand, we are basically able to understand that blockchain is nothing, it is a way of storing data, and it is a state machine means um, it has different states at every period of time, right? And the data is basically continuously changing based on the transactions we are sending to manipulate that data, right? Now, yeah, we already talked about transaction. So transaction is something that a user can send. So I can be a user, you can be a user, or any smart contract can be a user who can send transaction and manipulate the state of the blockchain, right? And once the transaction is verified and executed by the EVM, it triggers the changes in blockchain. So suppose I basically publishes a transaction to the Ethereum blockchain that, okay, I want to change the value of this particular variable from 5 to 10, right? So some processing happens in the background, and then it got verified by the every other people on the network, right? We will talk about that in separate video, but yeah. And then when the verification is done, the new state actually comes into the picture, and it basically updates the new state into the block with the new timestamp. So there will be new account balances, new account storage are updated, and like, so user sends a transaction, there will be a old state, and then transaction got processed, and then you will be getting a new state. And then furthermore, we will be following this particular new state for the most latest transactions. So this is how it works. So let's talk about who can send a transaction, right? So basically, uh, you as a user can send a transaction, and you as a user also initiate a transaction that is being proposed by a smart contract, right? So for that, what you need is a wallet, right? So what wallet is? So I believe you guys have used MetaMask, Phantom, or any other ledger wallet, right? So how it works is, a wallet has basically a unique identifier. It is derived from a public key, right? So there will be the pair of public key and private key, and the public key act as your global identity on the blockchain, right? And then there will be a balance. So what is balance, right? So balance is basically the amount of ether you are holding in terms, when we are talking about Ethereum, it can be different in any other chain, right? So when you send a transaction, you have to basically pay some fees. What is fees? We will talk about that later. But consider this like, you are basically paying the fees to the miner. Miners are nothing but the nodes that are connected to computer that we discussed earlier. They are processing your data, so they took some amount of fees. Okay, now let's talk about nonce. Nonce is basically a sequential increasing number. So suppose you send 10 transactions. So from 0 to 9, there will be a number assigned to every transaction. And that is there to like track the duplicate transactions, or like to resolve the race conditions and everything. So yeah, then there will be a private key. So private key is basically a secret key used to sign transactions, right? So basically, if you are holding that private key, so you are the owner of the transaction, and you are basically sending the transaction, and you have to sign the message, right? So that I can prove that you are sending the transaction. And then there will be a public key, which is basically derived from this private key, and it is basically your identity on the blockchain, right? So yeah, so I have added a illustration here. Okay, now let's talk about how wallet sends a transaction. So Ethereum actually provides you an API to interact with EVM, right? What that API is, that is basically a JSON RPC API. So why it is called as JSON RPC? Because the data you have to format is in JSON format, and it can be a HTTP API, it can be a WebSocket API, depending upon the provider you are using. So I'm using these terms. You will be understanding when we'll moving forward and learning more about this code. So we'll be understanding what provider is, what API is, what RPC is, right? But yeah, let's move further, right? So basically we have two things. One is ETH read call only, ETH underscore call, and then another one is ETH underscore send transaction, right? So how it works? So ETH call is basically the read only. So suppose if you want to use if you want to basically read any data on the blockchain without making any changes, right? And it does not cost any gas for querying any smart contract. Okay. But as we talked about, like we want to change the state of the transaction, state of the blockchain by sending a transaction, right? So you can send a transaction also, which allow you to change the state of the blockchain by transferring some ETH and calling the function to write the storage, right? It requires gas fees, and it updates the state of the EVM. Yeah. So both of the calls go through the Ethereum API, but only each send transaction results in state changes, right? So there is an illustration. So Ethereum API, and you can either call a read-only call, or either you make an send transaction call on the Ethereum. So yeah. So now let's talk about how Ethereum changes its states. Okay. So how it works is there will be a queue, and what are pending transactions. Suppose millions of users are sending transactions, right, in at a single time, right, and then they all can't be processed simultaneously, or you can say instantly, right? So what you have to do is, it basically have a queue where all the transactions are waiting. So we call it mempool, and that pool is basically to hold the pending transactions, and then the users, or not the users actually, but the miners can actually pick the transactions they wanted to include in their block, and then they process the transaction. So this is how it works. So then the pending transaction stays in the mempool until it get picked and processed, right? So when suppose we have two transactions here, like, okay, so this is a mempool. So first so how it works is, it works as a queue. So first in, first out. So transaction one comes first, and then transaction two comes second, and then so on. So the transaction one is the one who is going to process first, right? And it also depends on some various factor, like the gas fees and other things. But yeah, so suppose if you are sending a higher gas fees, then it is more, then there are more chances your transaction got picked first, right? So once the transaction is processed, there will be a state 0, then EVM updated the state to state 1, right? Then the next transaction, which is transaction 2, it has not been processed from state 0 now. Since the transaction 1 is already processed and verified, right? Now the transaction 2 is going to process on state 1. So it basically holds the state from the previous transaction, right? That is why we call it a state machine. So this is how it basically processes every transaction one by one. Okay. Now let's talk about the architecture and the execution model, right? So this is actually different from this mempool, so don't confuse. Okay. So Ethereum Virtual Machine is a stack-based virtual machine that handles the smart contract execution. It uses structured memory layout composed of stack, memory, and storage, each with distinct role. Okay, so this is a layman, like, I've added a definition in layman term, but yeah, let's talk about this. So EVM uses a last in first out stack to execute instruction. So this is different from transaction. So it uses a queue for processing transactions. So first transaction goes first out, but now here we are talking about the code execution, not the transaction execution. So every transactions comes with a state change, right? So suppose I deployed a smart contract. In that smart contract, there is a function to add variables, right? So suppose add a plus b, and that execution we are talking about here right now. So inside the transaction, there will be an execution happening, right? It can be a code execution, it can be any state changes, right? So that execution for now we are talking about right now. Okay. So for that, it uses a stack to execute operations, right? So if ever you have heard about the reverse polish notation, RPN, right? So it is how it works. So how it works is, like, it pops the value of the stack, compute the result, and pushes the result back on the stack. So I'll give you an example right now, and you will be able to understand it like very much in clear format. But yeah, keep this in mind right now. Okay. So let's talk about how EVM memory structure look like, right? So stack is basically a last in first out data structure, which is limited to 1024 element. So it can maximum hold 1024 element, right? And each element is 256 bits, which is 32 bytes. Okay, so like when blockchain creates a runtime stack, it maximum can hold 256 bits of memory for each block, for each element, and that element can go up to 1024 in every stack, right? So, and then there will be some another memory allocated, a linear byte addressable space that is volatile and temporary during the contract execution. So suppose when we are talking about arrays, right, array does not have a definite amount of storage, like it can go to a number of length, like it can go to 10, it can go to 20, right? So it also um, reserve some temporary volatile space that is linearly increasable based on the execution. Okay, and then we are talking about storage. So storage is where the permanent values are stored and it is persistent. So suppose your smart contract, your code has 5 variables that stores a value, right? So those have to store permanently, and right. So this storage is basically that place where the permanent values stored, and it is stored in a key value format, and every value is of 32 bytes, right? So this is how EVM execution look like. When you are basically calling a function, it actually process the data on top of these three memories. Okay, now let's move to the contract execution model. Okay, so we'll be looking into how step by step it works. The contract execution model: the moment you receive a transaction, so suppose you are a miner or you are the connected node in the blockchain, right? So you receive a transactions, right? You included all those transactions in your block. Now you have to process it one by one. Now you what it basically does, EVM sets up an environment, right? And it started converting that code into a byte code. Now byte codes are nothing, these are instructions. So what is an instruction? Let's talk about in a layman term. So suppose I and you are standing here, right? And I gave you an instruction, go sit there, right? So that is an instruction, right? And that is a single instruction that go sit there. So you'll go and sit there. So and that, so if you consider this as an instruction, I gave you an instruction in a code. You went there and said it consumes some synergy. So this is how it works. And also it also changes your state, right? So your code compiles into the byte code. That byte codes are set of instructions. It executes those instructions, and then there will be a state change or maybe a reversion. Reversion is basically comes when there will be an error, right? So suppose you are not able to sit there, you will come back and stand again and say like, let me know that I'm not able to stand, I'm not able to sit, right? So that basically you got an error and you revert back to original state, right? So whether it is state changing or whether it is reverting back to original state, the transaction is considered as completed, right? And based on the execution that are being processed here, the state changes or the reversion is applied to the new state. So mathematical representation would be like S and T. So S are the operations, T are the time, and then basically the new state will come, right? Okay, so let's talk about step by step. EVM sets up a execution environment. So basically, suppose you call a function in a transaction, suppose you call a add function. So how it works is it allocates some memory. Why memory? Because maybe the memory is required to process your data, right? And then it also initializes a stack, right? And then it also prepares the context for execution, where the execution of your function is going to happen. Now it comes to execution. So EVM runs the contract bytecode instructions one by one. So suppose your function is now converted to a bytecode, and that bytecode is step-by-step instruction. So I'll come to that, then you will be able to see it very clearly. And it manipulate the stack, it manipulate the memory, it manipulate the storage. So suppose it uses the stack to process the opcodes, right? And then it uses temporary memory if required, and then it manipulates the storage. Suppose we are adding two variables and storing it in the so output C. So A plus B equals to C, and C is the storage variable, right? We're storing it permanently. Then it uses the storage, and this continues until the transaction is completed or we met the condition, right? Now, termination can also happen. So if the program complete successfully, it returns the data. So if you have a return statement like return the output, it will return the data. If any error occurs, it will revert, right? It will also revert in case of out of gas. So what out of gas is, we'll also talk about it. Or it can also revert if you have an invalid opcode exception. Okay, so now we are going to talk about the gas cost for common operations in Ethereum and how gas actually works, right? So we already talked about this that when we basically execute any smart contract code, it converts into a low level language, which is basically a byte code, right? And then those byte codes are nothing, those are the set of operations in opcode. So opcode is basically termed as a single operation, and then the set of opcodes is known as bytecode, right? So you must have heard about this that whenever we write any language, like it, whether it be JavaScript, whether it be Python, whether it be like C, C++, Java, right? So it actually compiles first, and so yeah, for JavaScript it interprets, but yeah, for like for anything that compiles, whether it be C or Java, it compiles to a low level language, which computer can understand, right? So same goes for the Solidity. Solidity actually compiles first into the byte code, and then those byte codes are like the opcodes which are like processed in assembly. So this is how internally it works, and we will be seeing like how gas is actually decided and calculated based on those byte codes, right? So I already gave you an example about like me giving you an instruction, right? So suppose I gave you an instruction, stand there, right? So that consumes some amount of gas, right? Like some amount of energy, right? So while standing, you are basically going to consume some amount of energy. So similarly, when I ask you to go and eat, that is another instruction, but the energy you are going to consume must be different, but it will be constant, right? So for standing, you will be consuming a different amount of energy. For eating, you will be consuming a different amount of energy, right? So similarly, this concept works in this gas. So gas is the energy that we spend while mining the transaction, and that gas is basically specific to the instruction move we process, right? Now, so different EVM operations consume different amount of gas. So suppose we are adding and subtracting, it will cost us 3 gas. We are multiplying, dividing, it will cost us 5 gas. If we are storing a new value, so other than the storage, it costs us 20,000 gas. If we are updating a new value, it will cost us 5,000 gas. If we are creating a new contract, so suppose in Java you have heard about creating a new class like new car, new boy, right? So it is similar to that. We are creating an instance of a new class, a new contract. It consumes 32,000 gas. So these are the amount that it basically consume on these opcodes. So these are opcodes: add, subtract, multiply, divide, S store, update, create, right? These are opcodes. Now let's talk about the gas optimization a little bit. So imagine you are planning a road trip and you want to get to your destination while using the least amount of fuel, just like saving gas of on Ethereum. So like the more gas if efficient your code is, the more it is good, right? So suppose if you are performing any operation, so you must have heard about this in data structure and algorithm, that you have to reduce the complexity, right, of the algorithm. So it has to be O of n or O of 1, right? So order of 1. So the lesser the complexity of the algorithm, the lesser it will take the computation resources. So this is how it works here. So the lesser the amount of code, the more efficient the amount of code you write, the lesser it is going to consume the computation resources, and the lesser it is going to return in the gas cost. So this is how it works. So road trip elements, like you basically plan the routes, you select the vehicle, you manage driving technique, you do the load management, right? If the weight is more, the vehicle is going to consume a lot more food fuel, right? Same works in the Ethereum, right? So you have to write efficient algorithms, you have to use efficient data structures, like, so if you're using arrays, so for arrays you have to, for to find any value or to look up any values, you have to loop it again and again, right? But if you're using mapping, right, so you're using more storage, but you look up algorithm must be more efficient because it takes like O of one, right? So something like that. Then the code logic that minimize gas uses. So whenever you are writing any code, it has to be used, it has to be minimized to use the gas low. Storing only essential data in storage. So this is one of the crucial part, right? And this is something that actually determine if you are a good developer or not. It's Solidity developer. Like whatever data you are storing on chain means you are storing on the blockchain. Whatever data you are storing on chain, you have to decide what is necessary and what is not, and because every storage costs you some gas. So this is how it works. Now let's talk about some gas optimization technique. Use memory instead of storage. So like if you need some temporary variables to do calculation, so rather than storing them permanently, you can create a memory variable. Memory, I have told you earlier, we use three types of memory: stack memory, and another one was, what was that? Let's come to the, yeah, storage. Yes. So we basically like if you are doing any calculation and we need some temporary variable, to always define memory variables, not define storage variables, because storage variables are going to take permanent storage and those will cost us more gas. Then batch operations, right? So what happens is when you send transactions, so suppose you are making sum of two numbers, right? So you created a function called add, and it is taking input of two numbers and summing that and resulting in it a number, right? So when you do that one by one, so there is a basic gas fees every time you have to pay when you have to send transaction. So whether you are doing on anything or not, so like somewhere around 21,000 gas you have to pay every transaction, and that is the basic gas fees that you have to pay only, and it does not matter what operations you are doing. So and suppose you have to do five sums, right? So you send five transactions, so every time you are paying 21,000 gas individually for each transaction, right? But what if you create your logic somehow, you can do a batch operation of summing all those five numbers in a single transaction. Then what it will do? It will result in the base gas will be used only once, not the five times, because sending one transaction and your code logic is actually optimizing it to batch the operations and giving the result in a single transaction. So this is how it works. Use appropriate data types. As I told you, the example of the array and the mapping, right? Also, like here I have mentioned smaller types like uint 8 don't save gas due to 32 byte slot alignment. So I'll come to this when we talk about uint and all those stuff. So basically, you can store numbers, and numbers are multiple type. There are like 8-bit number, 16-bit number, 32-bit number, and it goes up to 3256 bits, right? So we have already discussed this, that the one block is of 256 bit, right? So suppose if you declared a number as 256 bit, like here, if you declared it as a UN 256, then it is going to take a whole block. It does not matter if you're storing 1, 2, 3, 4, or in numbers, right? Like it is going to take very few amount of bits, but you are allocating the space of 256 bit. But suppose if you have to store very small numbers, like suppose booleans, 0 1, right? And 0 1 is something that will come under this uint 8. Now what you can do, if you store it like this, then you can store more values in a single block, because block contains 256 bit, you are allocating only 8 bit, so remaining bit will be empty to include another variable. So this is how it works, like packing something into the box, right? Yep. And avoid unnecessary computation. So if you are declaring any constant, if you have some formulas or something, right? So you can predefine those as a constant, so you don't have to calculate them on the go while doing calculation every time. So this is the one way we can do that. So we'll talk about the gas optimization techniques a lot in detail in moving course, right? And but yeah, these are the small things that I wanted to cover before moving forward, right? And directly diving into the code. So yeah, now let's talk about code efficiency versus gas usage. Is a small um, chart which shows like the code efficiency grows, the gas usage will go down. So it's like inversely proportional, right? Now, let's talk about what bytecodes and opcodes in the EVM are. Okay. So bytecode is a low-level machine code that the Ethereum virtual machine actually runs. When you write a smart contract in Solidity, it gets compiled to bytecode, which the EVM can understand. I already told you this. So analogy, we'll come to the analogy here. So recipe translation. So recipe in English, right? We write Solidity, so recipe in English. Then translator compiles it to the cooking code and code the robot EVM understand, right? So I try to put a simple analogy here. Yeah. So your Solidity contract is like a recipe. The EVM is like a robot chef, right? And if it does not speak English, it only understand bytecode. So you write the recipe in English, it compiled into the bytecode, and now the instruction for the robots are ready to compile and process. EVM opcodes, the instruction set that we already talked about. The EVM opcodes are nothing the set of instructions. Each line of bytecode is made of opcodes. Each opcode is a byte of instruction from 0x00 to 0xFF, right? Represent a low level EVM operation. So these are predefined things that sits inside the Ethereum virtual machine logic. So suppose if the bytecode comes to 0x00, which means stop, so you need to halt execution, right? So gas cost is 0. 0x01 means add addition, which cost us 3 gas. 0x02 is equals to multiply. So this is what computer understand, and this is the like mnemonic representation of that, and this is what us understand, right? So we write multiplication, but it is going to convert into 0x02, and then the computer knows here like okay, we need to do a multiplication, so it will consume 5 gas, something like s load, s store, s return. These are the all the opcodes that computer understand, and these are the hex value of those opcodes. So if we want to load a variable from storage, suppose we in our code we represented uint a, right? So we are trying to fetch the value of a, so we need to load it into the memory. So S load opcode works here. So it's 0x54 and it takes somewhere around 200 gas. Similarly, there are other opcodes. There are multiple of opcodes. We are not going to go in deeply into that because it does not matter if we completely learn all the opcodes or not. We don't need that for the coding. Now let's come to an example. So when I write a function, this is a sample syntax of Solidity. Function add, you passes two parameter. One is uint a, one is uint b, and then you have some modifier and other things here like public. So you are telling that this function is going to be accessible to the public and through the contract itself. Pure. Why pure? Pure is basically every time it is going to return the same result if the inputs are same. So this is a if you have heard about the functional programming concept, so functional programming allow you to reduce the side effects of the function. So in this function there are no side effects. If you're passing 2 or 3, it is always going to be result in 5, right? So output is directly relevant to the input, so that is why it is a pure function. Then returns basically means return statement, what value it is going to return, and we specified uint. We'll talk about the syntax more in detail when we are going to learn about Solidity. But yeah, let's understand like this is a function which adds two value, uint a, uint b, and then it returns the output of the a plus b. Now, when we run this function, it is going to compile into a bytecode. So equivalent bytecode will be look like this. So here I have written the opcodes and the values. So when we did push one, it set up the stack frame, right? Then all those things, push 10x40, get function signature. Function signature is basically this. This is the function signature, right? So it converts it into some kind of this language, right? And we don't really need to understand this what this is. We just need to understand, okay, it's going to convert into the bytecode and how it works. Like, let's go. So we discussed about that the code execution work in a stack process, right? So when after push 10x01, which means the value 1 to be pushed. Okay, so push 1 byte to stack. So we pushed 2. Sorry. Yeah, so these are two variables. So let's consider the value of a is equal to 1, value of b is equal to 2. So uh, so this is the byte code. So 0x would be the hex representation, and then the byte code starts. So 60 means push 1 opcode, push 1 byte to stack. So I created a 1 byte of memory in stack. Now I come to next step. The value of 1 to be pushed, 0x01, means you have to push the value into the stack. So the value for a is equals to 1, so we push that. Right. Now the value of 2 to be pushed. The value of b is equals to 2, we push the value in the stack. So 1 and 2 are now in stack. Now we use the 0x01 opcode, which is add two top values on the stack. So 1 plus 2 is equals to 3. Now later on we need to just return this result, and the stack got empty. So this is how back in like machine, this is how it process the data, and we just need to understand like how it works. We don't really need to go deep dive into these stack operations, these opcodes, but yeah, when you are going to work on very gas optimization stuff, and when you're going to write very production level contract, then you have to have understanding of all these to optimize your contract further. But yeah, this is not something that we need at the starting. So this is like a very high level thing. Yeah, so I mentioned all the things like how this works. And there are also advanced contract creation flows, like when you deploy a contract. So like suppose you created a new contract, you created a new code file, and you wanted to deploy it on the blockchain so that everyone can use it, right? So the special transaction is sent with a constructor bytecode. So we'll talk about constructor, how what it is, but it is a type of transaction we send what allows EVMs to run a creation context, and it basically stores the runtime bytecode of that contract, and then it also assign a new address to that bytecode. So whenever basically we deploy a new code on chain, it converts and compile it to the bytecode and store that bytecode, and then it assigns a new address. So have you heard about APIs? So how APIs work is you have a URL, right? So suppose in your API you have a function defined, a controller function. So you have a specified path to call that API. So this is how it works. So you have a specified address to call that particular piece of code, and you can refer using that address. So this is how it works, right? So yeah, so this is all about Ethereum virtual machine and how it process the transaction, how it process the opcodes, how it set the context and execute smart contract, right? And this is a basic introduction I have given to you. Now moving forward, we will be learning more about other things, but yeah, this is your first lecture, and hope you guys liked it. And thank you so much for being here, like following me till here, and we'll be coming up with a lot more videos. So yeah, let's get started.